Shall we do the international activity or?
Just to check, Professor Pachori, Bilas Pachori.
EACH. Yes.
Is there?
Yes, yes. Both of them. No, no, you'll be sharing this mic.
Can we say
Make it forward.
so? Shall we start? Exactly. Two more minutes. So we can look from our own system or shall I go there
Ready to go there.
for the first lesson? Okay. Yeah. Whatever you say, we should sit here and do the three sessions. That is okay, not too hard. Okay. That's it. Sound is okay, na? Sound is perfect. Yeah, camera. Ah, yes. Just this Sophie, just send a message in the chat box. Welcome, Professor Pachori. Okay, now it's half 12. So welcome you all again to the first ever session of our International Faculty Development Program. And this session um, will be taken up by an eminent professor from IIT Indore. And we are really honored to have a distinguished expert like Professor Pachori. Uh, Professor Pachori immediately, accepted our invitation and uh, also gave his consent to deliver two lectures in this international faculty development program. So for that, we are really thankful to you, sir. Today, Professor Pachori is here to share his expertise on image and signal processing. His insights definitely is relevant to our current discussion on advances in machine learning, image processing, and NLP. He will speak on signal analysis based machine learning for EEG data processing today. So, without further ado, I would like to invite the moderator of today's session, first session, engineer Hisofi Angami, to moderate the session. He will give a brief introduction and will help to continue the whole session. Thank you. I welcome Hisofi to take over. Thank you.
Thank you, madam, for the time. So before we start, let me give a brief introduction about our resource person. Professor Ram Bilas Pachori received a BE degree with honors in electronics and communication engineering from Rajiv Gandhi Technological University, Bhopal, India in 2001. The MTech and PhD degrees in electrical engineering from IIT Kanpur, India in 2003 and 2008 respectively. Before joining IIT Indore, he worked as a postdoctoral fellow at Charles Dunet Institute, University of Technology of Troyes, France, 2007 to 2008, and an assistant professor at Communication Research Center, International Institute of Information Technology, Hyderabad, 2008 to 2009. He served as an assistant professor and associate professor at Department of Electrical Engineering, IIT Indore. Presently, he is working as a professor at the Department of am I audible? Is there any problem with the audio? Okay, okay. So currently he is associated with the Center of Advanced Electronics at IIT Indore. He served as the visiting professor at Department of Computer Engineering, Modeling, Electronics and Systems Engineering, University of Calabria, Rendi, Italy. A Faculty of Information and Communication Technology, University of Malta, Neural Dynamics of Visual Cognition Lab, Free University of Berlin, Germany, School of Medicine, Faculty of Health and Medical Sciences, Taylor's University, Malaysia. Previously, he worked as a visiting scholar at Intelligent Systems Research Centre, Ulster University, Londonderry, UK during December 2014. His research interests are in the areas of signal and image processing, biomedical signal processing, non-stationary signal processing, speech signal processing, brain computer interfacing, machine learning and artificial intelligence, and Internet of Things in healthcare. He is an associate editor of Electronics Letters, IEEE Transactions on Neural Systems and Rehabilitation Engineering, Biomedical Signal Processing and Control, and an editor of IETE Technical Review Journal. He is a fellow of IETE, IEI, and IET. He has 297 publications, which includes journal papers, conference papers, books, and book chapters. He has also 8 patents, 1 Australian patent, and 7 Indian patents. His publications has been cited approximately 14,500 times with H index of 65 according to Google Scholar. So without further ado, I invite the rest. I invite the resource person, Professor Ram Bilas Pachori, and hand over the remaining of the time to him.
Thank you very much for a nice introduction, and I would like to convey my thanks to Professor Sujata Das for providing this opportunity to be part of this faculty development program and also deliver this talk. Thank you very much. Let me share my slides. Is it slides are visible?
Yes, sir, we can see the slides. It's
Okay,
visible.
okay, okay. Thank you very much. Thank you. So, good morning, everyone. So, today's talk is on signal analysis based machine learning for EEG data processing. In this talk, we will see use of actually signal processing that actually can give you nice set of features. And like generally in the literature, you see the people like researchers use machine learning on the data, like in issue of using signal processing, and they do data classification, whether like you have multiple classes or two classes of the this EEG data, and only this machine learning when you use, then actually sometimes it is not easy to identify like what is inside, what is the level of the disease. So there is actually a lot of interest in the literature to use signal processing machine learning. So signal processing can give you more insight about the data, about the signal that you are analyzing. And in this actually talk, we will use multi-channel signal processing. So like brain, when you put electrode cap to record the EEG signals. So generally in literature, there is actually conventional way to consider each channel data or each signal from each channel, and then we process it. Here we will see actually our group has developed recently some frameworks which are suitable for multi-channel signal processing, and how this machine learning technique actually can be used together with this multi-channel signal analysis technique. So that actually, and we have actually proposed the framework for computer-aided medical diagnosis for the this epilepsy disease and schizophrenia disease based on these multiple this signal processing based approaches. So with this background, let us start this talk. So this is the overview of this presentation. First, we will see introduction. After that, we will actually see what is the motivation of this multi-channel signal processing. Then empirical mode decomposition, which actually we call EMD, that briefly will be explained. And also we will see what is the motivation for the development of EMD, and with respect to the other conventional approach that is already existing in the literature. After that, empirical wavelet transform will be explained, and then actually our group has proposed this multivariate empirical wavelet transform that also actually will be explained, and then its application for detection of epileptic seizures from electroencephalogram EEG signals will be presented. And after that, the iterative filtering is also another common way, actually another way to overcome the limitations of the EMD method. So for that also actually we have proposed multivariate iterative filtering concept that will be explained actually in this talk. And after that, this multivariate iterative filtering, its application for detection of schizophrenia based on EEG signal will be also presented. And in the end, a conclusion will be provided. This is actually one of the important part of signal analysis is to extract the information which actually these biosignals or unknown signals they carry. For examples like electroencephalogram, EEG signals, they carry information about the human brain, like whether it's normal or it has some disease like depression, schizophrenia, epilepsy, uh, uh, and like the common way that was proposed actually in 1807 by the Joseph Fourier, that to represent this unknown signal in terms of known functions like sinusoidal functions And these non-functions are known as basis functions, building blocks, and non-signals. Uh, and if you like simple functions, simple signals, and if you represent this complicated signal or unknown signal in terms of the non-basis functions, then actually our problem becomes simpler. This unknown signal is represented in terms of simple functions, and that these functions we know. So in that way, actually, we get lot of information about the signal because we have projected this unknown signal in terms of non-signals, and the projections give you a lot of information about the frequency domain and Fourier transform. So we time domain signal, we get frequency domain using such kind of basis functions which are known to us, which are generated by us. So here two examples you can see in the slide. First one, it is actually signal. This is mixture of two frequency components, and like superposition of two frequency components. So at any point of time, these both frequencies are present. The next one you see this signal. This is concatenation of two frequency components. Like first 0 to this particular point of time, you have one frequency, and then from this point the end of this signal, you have another frequency. So the first signal is actually stationary signal, and second signal is non-stationary signal. So when you apply Fourier transform for this stationary and non-stationary signal, then you see you have same spectrum, same Fourier spectrum. So this is actually one of the serious problem with the Fourier transform when you are defining signal as a stationary and non-stationary signal, because there is no time information. You see the frequency domain, that is actually it should be unique for different signals, but here it is not unique. It is same for stationary signal as well as for non-stationary signal. So due to that, actually, there has been a lot of interest in the signal processing to define basis functions in such a manner so that this representation is unique. So like for stationary signal, you will have different time frequency representation, different spectrum representation, or for non-stationary signal, you have different frequency representation. So based on that, actually, concept, there have been two directions in the literature. In first direction, but the whole purpose of this research is to develop basis functions which are actually non-stationary in nature, so that they can be able to handle the non-stationary signals and can provide the better analysis to or extract the meaningful information. So the first class is fixed basis function. So where actually we design basis functions from our side, and then we represent actually such signal in terms of such basis functions which we have designed. So such kind of methods include Fourier transform, wavelet transform, uh, etc., and like flexible analytic wavelet transform. So there are tunable Q wavelet transform. There are various actually now new approaches are coming where we use actually the basis function in more general way so that it can represent non-state signal in efficient manner. Now, new direction that is actually very interesting, and there is a lot of interest in these days, that is adaptive basis functions. So, like instead of designing basis functions from our side, uh, we actually extract these basis functions from the signal itself. So, we call them intrinsic mode functions, IMF. And such kind of examples, they are like empirical mode decomposition, empirical wavelet transform, variational mode decomposition, etc. And these both directions actually are open for the research, and people are trying to develop the basis functions which can provide better representation of the signals, and such signal representation is actually very useful with the machine learning approaches. And you see in this talk how very interesting results we can get once we do this signal analysis together with the machine learning. And the more actually now we will see little bit mathematical part, and this basis function, that whatever we are designing from our side or obtaining from the signal itself, then that actually this is at this mathematical form. So ut equals to at e to power j phi t. So this at is time varying amplitude and phi t is time varying phase, and if you perform derivation of this phi t, then you get instantaneous frequency. So in that way, this is amplitude and frequency modulated sinusoid. That is actually suitable for narrow band signal, and that is the first actually This is the first model, and little bit if you go more general model of this, so then we go for multi-component non-stacy signal. So that is actually wideband non-stacy signal. So this is another example. X equal to sum of these all such kind of monocomponent AMFM gives you the multi-component AMFM signal or wideband signal. So this here each AMFM component actually is a general form of the sinusoidal functions, and that we use in Fourier transform, and it represents narrowband signal, like narrowband in the frequency domain. Instead of the basis functions that we use in Fourier, that is sinusoidal functions, they represent only one spectral line. So here actually this each basis function has now the frequency range, and then you when you combine all the frequency, the AMFM count which are disjoint, and then you will represent wideband signal. And these both models are for univariate data. So like you have only single channel data. Now we can go for multi-channel scenario, and then this matrix gives the n variate monocomponent signal. So like this is multi-channel signal, and each channel or each element of this vector, that is actually monocomponent AMF. So now we can generalize this n variate monocomponent signal one more further step, and where we have multivariate multi-component signal. So each element, each channel is actually wideband signal. So like earlier it was narrowband signal, that is wideband signal, or in other words it is multi-component AMFM signal. So now your signal is multi-channel in nature, and each part or each element or each channel, that is also wideband. So this is more general model, and that is actually this is for our interest in this talk, and we will see how to actually handle such kind of actually mathematical model when you use adaptive signal processing approaches. So in the real life, actually, you will find many scenarios where there is a presence of multi-channel signals. So like you can see in the slide, there are actually there are many scenarios, but for just example purpose, we have actually selected only three. And the first one is this vibration signal processing. So where actually we are interested to detect the fault of the gears or machines with the vibration signals. And here you can see in issue of gun sensor, you can use multiple sensors, and you can have multiple sensors to detect the gear fault. And second case, this is actually electroencephalogram, EEG signal recording, and where actually we put electrode cap on the human brain, and it has multiple electrodes, and from the different electrodes we can record the multi-channel EEG signal. In third scenario, that is actually electrocardiogram ECG recording, and here also we put actually multiple electrodes on the chest of the person, and at a time we can record multiple signals, ECG signals. So in all scenarios, that is actually it is possible due to development of the technology. Now we have actually there is a lot of advancement in the sensing technology. We have multiple sensors, so at a time you can record multiple signals. And also if you actually analyze these signals channel wise separately, then these channels actually they are highly correlated. These signals whatever we record from the each channel, they have some correlation, and also they have some mutual information. So that actually we ignore if we consider this conventional like single channel processing or univariate signal processing. So due to that, there is actually a lot of interest in the literature to use multi-channel signal processing. So at a time, you can actually analyze all signals together. So like all vibration signals can be analyzed together, all EEG signals can be analyzed together, all ECG signals can be analyzed together. And so that you can preserve the mutual information which these all channels have, and also you can preserve the correlation. And other thing actually, due to these reasons, there is another area of research is coming in signal processing, that is time frequency analysis of multi-channels. So this is like multivariate time frequency representation. There's new area of research is coming, and we have proposed one framework that is actually in this talk that we will see, and for time frequency representation. And this is actually, these are the motivations for this use of multi-channel signal. There is another motivation, this mode alignment property. So like these days, this the second direction I mentioned, where we use adaptive basis functions. So these adaptive basis functions we are extracting from the signal itself. So this due to adaptive nature or data dependent method, each channel actually will give you different number of intrinsic mode functions, different number of components. So for example, like one channel has five components, other channel can have 10 components, other third channel can have 7 components. So comparing all of them together, it is a problematic task because they are not same number. So due to that reason, in order to preserve this mode alignment property, we want to have same number of components, and each component of the different channels will represent the same frequency component. So that is also one of the actually important motivation for developing this multi-channel signal processing technique. So in this talk, actually, we will see these two multi-channel signal processing framework. One is based on multivariate empirical transform, and second one is on based on multivariate iterative fit tree.
But for us, child is 14, na?
Yes, I think
Now, actually, this empirical mode decomposition that was proposed in the literature in 1998, that has changed the direction of signal processing. And what is the actually need of EMD? That just briefly I will explain it, and then we'll go for the further part of this actually EMD and advancements. So actually, this Fourier transform was the simplest technique of signal analysis that was proposed in 1807, and where this Fourier actually represented signal in terms of sinusoidal functions. And these sinusoidal functions, they are periodic in nature, and they have infinite spread. So they exist from minus infinity to plus infinity. So resolution actually of the signal in time, for example, in time domain, depends on the spread of the signal. So the spread of the signal in time domain, that is infinite, and due to that, resolution of the sinusoidal functions in time domain is actually zero, because it is inversely proportional to the spread in that domain. So in frequency domain, the sinusoidal functions, they have actually zero spread, so that due to that, resolution is infinite. So the sinusoidal functions, they have infinite, they have very less or zero resolution in time domain, and due to that, they are not able to represent non-static signals. Non-static signals means in signal processing, we use mathematical models to represent the signal. If any of the parameter is changing with time, then we call them non-static signal. So the sinusoidal functions that we use in Fourier transform, they don't have this time varying property. Their parameters don't change with time. So due to that reason, this Fourier transform is not suitable for non-stationary signal processing. And in order to use this Fourier transform for non-stationary signal processing, the short time Fourier transform, which we call STFT, it was proposed in the literature, where we divide this signal into different segments. And each segment, actually we assume that signal is stationary, then we apply Fourier transform, and the arrangement of these Fourier transforms of the all segments gives us short time Fourier transform. In short time Fourier transform, there is no thumb rule which will suggest us what should be the size of the window and type of window. So like if you have low frequency component, then you need wide analysis window, and if you have high frequency component, then you need narrow analysis window. So that flexibility is not there in the STFT. In order to have that flexibility, or in order to have more like multiple resolution or more flexible analysis, where this scale concept was proposed, that is known as wavelet transform. Then there actually this scale we choose according to the requirement. So like a low frequency component can be analyzed with large scale, which gives you the poor time resolution and good frequency resolution. On the other hand, high frequency can be analyzed with the low scale, which gives you good time resolution and poor frequency resolution. So in that way, actually, this multi-resolution analysis can be studied and for the given signal, and it's very interesting approach, and lot of actually work has been in the literature using wavelet transform concept. And one important thing with the wavelet transform is that actually this wavelet transform can be implemented with the help of filter bank. So you have signal just it is a filter bank of two step like two channel filters, low pass, high pass, and down sample by two every part. That is one is gives approximation, other channel gives you the detail. Further, you can apply this two channel processing and similar way that you can implement the wavelet transform. And the problem actually in this discrete wavelet transform that we call that is filter bank approach, we don't know which mother wavelet is suitable for the data analysis which we are doing. And also the number of labels required for the decompose, that is also not clear. There is no thumb rule which will suggest us that for this particular signal this much level of decomposition is required. So those all actually based on the trial and error or based on the some more study required to use them in the signal processing. So due to that, actually, this all whatever till this point you have seen this wavelet transform, short time Fourier transform. In all cases, we design basis functions, and this with the real life signals actually we represent in terms of these basis functions. So this is the case in 1998. Motivated by these actually these problems that I mentioned in the earlier decomposition, this Huang and others, they come up with the new approach that is empirical mode decomposition. This is the data dependent approach. Instead of using mathematical formula for analysis synthesis like in sine Fourier transform, wavelet transform, short time Fourier transform, here actually even algorithm is used. You just apply algorithm on the data and which will decompose this data into in the form of this intrinsic mode functions. So the algorithm is very simple. You have the signal, then you identify all the maximum minima, then you interpolate this maximum minima, get two envelopes corresponding to this maximum minimas, and then you take average of these two minima envelopes corresponding to maximum minima, and then you subtract from the signal, that is known as the details. And this detail or residual actually is checked for the required conditions to define intrinsic mode function. So there are two conditions. One is number of extrema and number of zero crossing. They should be defined at most by 1. So this condition ensure that whatever intrinsic mode function you have is obtained, that looks like sine cosine function. And second condition is actually the average value of the intrinsic mode function is 0. So this condition ensure that whatever IMF you have derived, that is actually symmetric in nature. So these two conditions ensure that at IMFs whatever you obtain, they are symmetric in nature. They are look like sine cosine function. And this process is continued till you get the first IMF. Once you get the first IMF, then you subtract this first IMF from the signal, actual signal, then you have to get the residual, again repeat the same process, this algorithm, and then you get the second IMF. For the third time, you subtract first IMF, second IMF from the actual signal, then you get the residual, then repeat the same process. So in that way, we actually obtain all possible IMFs from the data, and last part, when you are not able to get the IMF, that we call residual. So this is one example here, signal, and then actually these are the obtained IMFs. So first IMF to this eighth IMF. So these are the highest frequency to lowest frequency, they are arranged. And this first IMF, this is also known as the lowest scale present in the data. And eighth IMF is the highest scale present in the data. So in that way, first IMF is also known as details, and second eighth IMF is known as approximation. So these are all actually these frequency components are arranged in such a manner. And based this empirical mode decomposition for this also actually extended in the literature for multivariate case that are complex EMD, rotation invariant complex EMD, bivariate EMD, multivariate EMD, fast multivariate EMD. So there are a lot of versions actually have been proposed in the literature, and one of the actually the important problem with this EMD that is actually it lacks mathematical theory. It is just like algorithm, and also in addition to that, there is when you use this in real life signals, then researchers have seen it suffers from mode mixing problem. So these two major actually problems actually this EMD method has, and to overcome these two limitations of EWT EMD method, this empirical wavelet transform, which we call EWT, was proposed in the literature, and that actually we have extended for multivariate case, and then we applied for epileptic seizure detection. So these EEG signals that actually they are recorded from the human brain, and human brain is highly complicated and nonlinear system. And the electroencephalogram, which we call EEG, they signal major electrical activity, which is generated by the neurons in the brain. And epileptic seizures, they are the outcome of the transient and unexpected electrical disturbance of the brain. So in the brain, this all neurons they synchronize together and they generate very high electrical activity. And due to that, actually, brain becomes unbalanced, like this very high current, electrical current. So once brain is disturbed, then everything is actually disturbed in the body because brain is the master of the body. And epilepsy affects around 2% population of the world. And the EEG signals are commonly used for the diagnosis of epilepsy. And in this work, actually, that we'll see in this talk, that we have proposed empirical wavelet transform based approach for patient-specific epileptic seizure detection using surface EEG signals. So here you can see this human brain. There are four lobes: frontal lobe, parietal lobe, occipital lobe, and temporal lobe. So these all lobes actually they represent different activities of the human body, and in order to record this electrical activity for the all regions of the brain, we use 10 to 20 this electrode positions at the international recording system. So which is a set of electrodes, and we put on the human brain, and we give file. Each channel gives the different wave EEG activity. So here you can see, just for example, this two channel EEG signal. So this can be 256, this can be 12. This depends on the number of channels you are considering for recording. So motivation for empirical wavelet transform, already I mentioned, like the CMD method suffers from mode mixing problem, and also it lacks mathematical theory. So recently this EWT method has been proposed to overcome these limitations of EMD method. And when you see EWT in like in broad manner, just it needs three main steps. So first step is we obtain the Fourier spectrum in the frequency range 0 to pi for the analyzed signal, and based on the Fourier transform. And this is just in order to compute fast manner Fourier transform, is fast Fourier transform in the computer. And then we segment the Fourier spectrum into n contiguous these segments based on EWT boundary detection method. So in that way we determine the boundary frequencies. Once you know the boundary frequencies, then actually we define the wavelets, and which we use as band pass filter to each this each part, like each segment, and then actually we separate out these intensity mode as IMFs. So that actually that in that way, so our contributions like includes like extension of EWT method for multivariate signals, and time frequency representation of multivariate signals based on empirical wavelet transform or EWT with application to epilepsy detection. We call it empirical wavelet transforms because empirical, like we use maximum minima in EMD method, empirical mode decomposition in time domain. On the other hand, here actually we are using this maximum minima type of concept in frequency domain. So we are segmenting actually this spectrum, different segments, and each segment we are separating out using this wavelet filter, so that like in mode functions. So this empirical wavelet transform, if you apply, for example, you have this YT, it's a multi-channel signal, and Y1T is like one channel of like single channel, Y2T is another channel like YMT. So this M channel signal. Now, if each channel, if you decompose using this empirical wavelet transform, then actually you will have different number of IMFs, because each channel will have different Fourier spectrum, different boundary detection, and different design filters. So as a result, you have different number of IMFs for each channel. So there is a problem. So in order to have mode alignment, and in order to have same number of IMFs by the each channel, we have proposed that instead of using this uh, same different Fourier spectrum for the different channels, let us go for the average Fourier spectrum, and that is actually that we can compute from the Fourier transform of the all channels, different channels, individual channels. Then you average out, and then average spectrum you use to design the actually design the detect the boundaries and design the band pass filters or wavelet filters. Then you apply these design filters to each channel. So in that way, each channel will have the same number of IMFs and more alignment property will be preserved. After that, once you have components from the different channels, then you can actually apply Hilbert transform separation algorithm, which will give you standard amplitude and standard frequency. And here you can see once you have standard amplitude and frequency for the different modes for the different channels, then for each mode we can actually determine the joint instantaneous amplitude and joint instantaneous frequency. For we are using multi-channel combining multi-channel. So here you can see this mathematical expression. We have actually determined joint instantaneous frequency, joint instantaneous amplitude using this combining all estimated amplitude, instantaneous amplitude and instantaneous frequency for all the channels, and then we call it joint, and this is for one particular mode. And then based on that actually we can compute the time frequency representation, and we can generalize it for the all modes present in the data. So so for the all the oscillatory modes or levels, its time frequency representation can be defined by using this expression. So in that way we can have actually multivariate time frequency representation. Since this epilepsy actually that is actually this amplitude information is significant. So like when this epilepsy disease, and if you go to hospital, doctors generally see the two important features of the EEG signals. One is like spikes present in the EEG signal and also large amplitude. So motivated by that, actually we have proposed the features which are also based on the joint instantaneous amplitude. So like mean of the joint instantaneous amplitude, mean monotonic absolute amplitude modulation change, variance of monotonic amplitude modulation change, and all these three features mathematically drive mathematical expressions you can see in this slide. This is for the first feature, second feature, and third feature. So based on this actually concept, now you can see the proposed epilepsy seizure detection system, and which has been studied on PhysioNet CHB MIT scale PG database, and this recorded for 23 patients, and it has recording from 23 channels. So if you use all 23 channels together, then actually this method suffers from computational complexity. So out of 23 channels, actually we have suggested channel selection criteria, and in that actually you can select first channel with the least standard deviation, and other four channels are selected based on the relatively higher mutual information with the first selected channel. So in that way you can have five channels, and once you have five channels, then you apply this multivariate empirical wavelet transform where filter is designed based on the mean spectrum. And then you have actually the five channels, each channel will give you 10 modes, same number of modes. And then for five channels, each mode we determine instantaneous amplitude and instantaneous frequency, and then we determine joint instantaneous amplitude and frequency of each mode. And then from that we have extracted features from mode 1, mode 2, mode 10. And then actually we will see in the coming slides that there is a need of feature processing, because this is surface EEG signals based epilepsy detection. So surface EEG signals, they are actually they suffer from noise, and the analysis actually the features you will find they are noisy. So if you use feature processing, then this noise can be reduced, and in other words, the separation between seizure and seizure free parts can be improved. So after that feature processing, processed features, they are given as input to classify, where you can actually nicely detect seizure and seizure free parts of the EEG signal in automated manner. And such kind of actually concepts are very useful when you have actually like patients are like for example driving a car and he or she is going to have epilepsy attack, and such method can detect the seizures in advance and the required medicines can be given, and that way this actually attack can be bypassed. So here you can see this is 5 channel EEG signal and seizure case, and this is 5 channel EEG signal seizure free case. When you see the multivariate time frequency representation in case of seizure, then actually there is a presence of low frequency and high frequency components. On the other hand, if you see the time frequency representation for the seizure free case, there is absence of the high frequency component. So this time frequency representation can be used as a signature to detect the seizure and seizure free parts of the EEG signal in automatic manner. So like these signatures can be actually obtained using smartphones, in desktop computers, laptop, etc. And they are one of the important part in computer-aided medical diagnosis. And after that, these features, vectors from different noisy levels, they you can see here, and for the 10 modes, and this is second feature and third feature. And they are suffer from noise, they are noisy features. Then we have suggested use of moving average filter. So once you apply moving average filter, then enhanced features you can see this is like a smoothed feature. Feature 1, feature 2, feature 3. Then we have observed that if you multiply all of them to perform HUDMUD product, then you will have very good localized detection of the seizure. This is one of the beauty of the signal analysis. And when you multiply these all features together, or the all modes in the all 3 cases, then actually we have joint feature vector 1, 2, 3, and then you see the signal analysis is able to detect the seizure or epileptic seizure in very localized manner. And then these are given as actually input to machine learning classifier, that random forest classifier, and to detect the epileptic seizure in automated manner. And from the raw EEG signal, you can see this seizure onset is not clear due to lot of noise. But when you do proper signal processing and analysis, then actually you can detect that region where this actually seizure onset is taking place. And then actually we have compared our method with other existing methods in the literature, where researchers have used various signal processing machine learning techniques. And the proposed framework that is actually based on 3 features, and multivariate empirical wavelet transform and random forest classifier, which actually considers only 5 channels and 10-fold cross validation. It provides 99.57 specificity and 97.91% sensitivity and 99.41% accuracy. After that, there is another actually approach in the literature that is known as iterative filtering, which actually has been proposed to overcome the limitations of the empirical mode decomposition approach. So we have also extended this iterative filtering for multivariate case that we call multivariate iterative filtering. Then actually we have studied that method for schizophrenia detection. And in this part, we have proposed the separation of the rhythms using this multivariate filtering. So now rhythms actually will be multivariate in nature. So similar like signal will be multi-channel, your components will be multi-channel, your rhythms will be multi-channel, and that is actually another paradigm of the biomedical signal processing. So iterative filtering technique subtracts out the selective part of the spectrum in order to obtain the mode one by one iteratively. So here actually we design this filter. So this filter cutoff frequency, it depends on the filter length. So cutoff frequency is inversely proportional to the filter length. And length is computed by this mathematical expression. So where n is the sample size of the data and k is the number of extrema. So this like you have high frequency components, the number of extrema will be higher and L will be less, and as a result, cutoff frequency is inversely proportional to 1 L. So this cutoff frequency will be higher. So that is suitable for the high frequency component. So here then it is the X the signal that we want to analyze, and LX the filtered signal. Then we subtract this signal minus this design filtered part. Then you have residual, and you do this sufficient number of times or trials, then you get the first IMA. Then according similar to EMD, you subtract this IMF from the first IEM from the signal, then you get residual, and again repeat the same process. So in that way, you get all possible IMF from the signal. So for iterative like univariate signal, this you can see this way. So this just for an example to explain iterative filtering. This signal has got three IMFs, and then you have this is the design filter, and then you filtered signal, this filter, and you subtract this filtered signal from the actual signal, then you have the first IMF. Now first IMF is subtracted from the actual signal, it's all in frequency domain, and then you have the residual, which is actually suitable for the second IMF, the obtaining second IMF. So that is a residual, which is obtained by signal subtract the first IMF subtract from the signal, that residual, and again you design the filter. Then filtered signal, that filtered part is subtracted from the signal. So like that is after this removing this filtered part, then actually you have the second IMF. First IMF, second IMF. Now both are actually subtracted from the signal. Then we get the residual. There is the third IMF. So in that way, actually, the every like this IMF every time this is for univariate time. So this is the first, second, and third IMF. And now this actually how to extend this concept for multivariate iterative filtering. So this is actually flow chart for iterative filtering. You have signal, then find the number of extremas, maximum minima, then determine the filter length, and based on length you determine the cutoff frequency. Then you design the filter and subtract this filtered part from the signal. Then you have the residual. Then there are two stopping criteria: standard deviation, that is consecutive iterations. That if it is around 0, then we stop it, and if it is more than 3, then we continue. If it should be less than 3, then we will stop it. So that is actually threshold. If it is becoming around 0, then we can stop it. This is first criteria. Second stopping criteria, number of extremas. If less than 3, then we can stop. So this is actually this is for univariate iterative filtering. Now when you extend this for multivariate iterative filtering, then you can see signal, and then actually now each channel will have different number of extremas. So as a result, different filter length will be there, and different cutoff frequency will be there. So number of IMS will be different. So in order to overcome this problem, we have suggested use the maximum number of extremas from all channels. So that is actually k equals to maximum e, and then based on this number of extremas, we determine the length of the filter, and determine the cutoff frequency, and design the filter and subtract from the signal. So that residual, and then actually these two stopping criteria that actually can be used, and then in that way we use the multivariate intrinsic mode functions. That is actually from the multi-channel signal. So this is one example. Here you can see. So this is a two-channel signal we have considered, and each channel, now in the first channel it has 2 IMF, second channel has first only 1 IMF. And now if you do it individual channel wise, then this is the design filter here. So the both are different, and now we will take the maximum highest of this out of the like these two channels, the filter which has the highest frequency. So this first this filter will be selected that we use for the filtering, and then actually this part is subtracted from the signal, is filtered here, and then this is the first IMF. Now first IMF is the two channel IMF. This will be subtracted from the signal to get the actually residual for the second IMF. Now here also again you design the filter for individual IA channels, then you find the maximum of both. So this is the maximum cutoff out of these two filters. This has got maximum cutoff frequency. So we will select this one, and this one is used for the filter out both channels, and then filtered signal is removed from the actually these two channels. Then it's the second IMF, and the same way we have actually subtracted first IMF, second IMF from the signal, and then we get the residual for the third IMF, and this is same now. Now both filters are same here. So design filter. So we take one of them because both are same. So then actually subtracted that one, and the third IMF. So in that way, your signal is actually a two channel signal, and the first IMF, second IMF, third IMF, all are also two channels. That is actually example of multivariate iterative filtering. So this is a very interesting concept, and actually it can be used also for decomposing the multimodal biomedical signals. So like in ICU, we record signals from many modalities, like many modalities. One of the example here, in this 4 signals are recorded in the ICU. First one is recorded from the ECG lead 1, from lead 2 ECG signal, and third one is breathing signal, and fourth one is seismocardiogram signal. So these four signals actually they have different information, but if you use multi-channel signal processing, multivariate iterative filtering, then you can actually get the correlated information in terms of components, and that is actually you have the IMFs which you obtain. They have similar frequency components in all modes, all modalities. So here you can see this is a multivariate in iterative filtering for ECG 1, 2, breathing, cardiogram signals, and 11th IMF shows the actually the same frequency component that is actually taking place in all the signals. So seismocardiogram is different than the ECG, breathing signal is different than the ECG, but you find that all actually the correlated information can be represented by multivariate multivariate decomposition techniques. So this common information can be actually obtained from the all modalities that can be give reliable measurement of the biomedical markers, biomedical information which may be required for the surgery or treatment. So after that, actually this concept, we have studies for schizophrenia detection from EEG. Schizophrenia is a chronic and severe mental illness, and it affects around 20 million people worldwide and 1% of world population, and more than 1 million people in India. Symptoms for the schizophrenia includes hallucinations, fixed false sleep, hallucinations, experience of seeing, hearing, tasting, smelling, or feeling that does not really occur. Disorganized speech and thinking, abnormal motor behavior, and this is the proposed block diagram of the schizophrenia detection method. And here you see we have multi-channel signals, and we take 25-second segments for the processing. Then we apply pre-processing, then the iterative filtering for multi-channel EEG. Then for the all different channel we have different modes, and then actually we have proposed rhythm separation. That is very interesting. Now these rhythms are multi-channel in nature. So delta, theta, alpha, beta, gamma. They are multi-channel rhythms. Then we have extracted features from the EEG rhythms. Then we perform classification using machine learning. Then it gives you the automated classification between schizophrenia and healthy subjects. For the study purpose, we have taken actually this publicly available database from the Institute of Psychiatry and Neurology, Poland, and this has actually schizophrenia 14 patients and healthy 40 subjects for the recording purpose, and 19 channels were used for the recording, and sampling rate was 250 Hz, and duration of these signals is around 15 minutes. And here you can see, for example, 3 channel FZ, CZ, PZ, EEG signal, and these are the obtained second, third, and fourth multivariate transient mode functions. So you can see for each case, all these 3 channels are showing the same frequency components. So this mode alignment property is preserved that also can be seen in that from the frequency spectrum, and they are actually all these components. They are showing the same frequency. And then actually we are using this mean frequency concept. We have actually separated out these rhythms, and each rhythm, delta, theta, alpha, beta, gamma, they have different frequency bands that you can see in this slide. And based on the mean frequency, if it is lying in this range, then we have included that particular component in the summation in order to have the particular rhythm. So in that way, we have separated out, segregated this rhythm, delta, theta, alpha, beta, gamma rhythms. And here you can see this delta for 3 channels, theta is for 3 channels. So each rhythm is now multi-channel rhythm, and that is actually a new way of signal processing. Most of the places in the literature you will find people use this univariate rhythms only single channel rhythm, but here you can have multiple rhythms. After that, actually, we have extracted features, Hozort activities or mobility and complexity from these rhythms. Then in that way, total features we have 285. Then we have actually used Kruskal statistical test in the student t-test, and we obtained the p-value less than 0.05. Then based on that, we ranked the features, and we found the best 30 features as a statistically significant features for the classification purpose. So here this was for example, we can see these 10 features, they are discriminative in nature, and with box plots it is clear that they are healthy as schizophrenia, there is clear cut discrimination, they are showing good discrimination. Then so they are powerful feature in terms of the discrimination between schizophrenia and healthy classes. So for the classification purpose, we have used the best 30 features, and then this following classifier SBM with cubic quadratic linear kernels are used, linear discriminant, k-nearest neighborhood, recently classifiers. And if you use this 30, based on trial and error, you found 30 features, this we are getting 98.90% classification accuracy. So for the performance evaluation, we have used accuracy, sensitivity, specificity, and positive predictive value. These are actually performance measures, and then you can see for the best 30 features, five-fold and ten-fold cross validation has been studied, and this various classifier SBM with QBA, quadrature, linear kernels, and this linear discriminant, k nearest neighborhood, decision tree, and you see we have computed accuracy, sensitivity, specificity, positive predictive value, and this area under ROC curve is also included as a performance measures, which actually it is ideally it should be one, and it is approaching one, it shows better classification. So here you can see from this table, this SPM with cubic kernel and with tenfold cross validation is good classification performance. Then we have actually compared our method with other existing methods in the literature. And here you can see actually the authors in the past, they have used various signal processing machine learning techniques, and they have got different performance. And our proposed framework that actually gives you very good classification performance, that is accuracy 98.90%, sensitivity 99%, and specificity 98.80%, area under ROC curve that is 0.999. So this is the conclusion of this entire talk. Proposed multivariate empirical behavior transform and multivariate iterative filtering are able to decompose multi-channel multivariate signal into meaningful components. Mode alignment is the most important properties of the multivariate decomposition methods. Proposed methods properly align the similar oscillatory components across different channels. And the proposed methods actually have provided with good detection performance for epilepsy and schizophrenia diagnosis based on the scale PEG. And the proposed automated frameworks can be useful for assisting neurologists in their decision makings. And the computer smartphones with the proposed algorithms can be used for the diagnosis of the neurological disorders in rural areas where they have shortage of doctors. So actually these whatever methods we have proposed, they are in the form of algorithm, and they can be used in the form of the app or the computing devices like smartphones. A smartphone will become really smart because it can detect these diseases at the initial level. So very useful for computer-aided medical diagnosis. So this talk actually based on the our this recently published two papers, and if you want to have more information about the presented work, I request all the participants please go through these two papers, and thank you very much. Any questions, please?
Thank you, sir, for an insightful talk. So now the floor is open for questions. If anyone is having any question, please ask. You can also post your question in the chat box. So I believe there is no question from the participant side.
Okay. So actually, yeah.
Can I ask you one question, sir?
Does it make
Sir,
any
I
difference
have.
if we may use
Uh,
different techniques for decomposition with multiple
can I
models?
ask you one question?
Yes.
Yes, some questions.
Yeah. So actually, yeah, this was different techniques will give you the different components. So you have to find out which technique is actually better for your technique. Like this selection of the spoon depends on the type of food. And if you want to have noodles, then you use fork. So because your food is discontinuous and spoon is also discontinuous. So similar way, actually we have to study and suppose the kind of features you need for your the data, accordingly signal processing technique can be used. You can study for your database whatever data modalities, and then you find out which one is best for you. Or if you know insight of the data, then according to that insight you can use the signal processing technique. Is it clear?
Hello, any more questions?
Unmute.
Any more question?
Yeah, let us say is EEG decomposed BW and ECG with band pass filter. So both are actually different approach. So you will have different components. So like when you are decomposing using discrete wavelet transform, then you are having this non-stationary basis functions. And when you are using band pass filter, then is a this is different stationary approach, different band that you will extract it with the like stationary kind of approach. So in both cases, output will be different. So DWT, you are actually designing basis functions which are like suitable for non-stationary signals, and band-pass filtering simple like is based on Fourier spectrum, that is stationary concept.
So any more question? Sir, I have one question.
Yeah, please.
When we are dealing with signals, EEG or ECG signals, being computer professional, um, instead of applying this EMP or EWT, can I convert the signals into image and apply deep learning like CNN or some pre-trained
There
training
is,
model?
for some people actually, like I have seen, like even one of our paper, some BTech students, like 10, they have 12 lead ECG, and just they have taken actually image of that, and they have given this as input to CNN, deep learning algorithms. That is actually just for classification purpose, it is fine, but you will not get insight about the data, what is the level of the disease. Like if you use signal processing, then you will get more insight. Like in one of the part in the initial talk, you see the location of the seizure can be detected. But using this image, you just can do classification only. You know that whether this person has normal or abnormal activity. Other things is difficult to know. But when you use proper signal processing, you consider them proper signals, then you will understand the information about the system from which these signals are generated. That is important.
Sir, I think after feature selection,
Yes.
while applying CNN, we can extract the features, and then the features, can be converted to again signal, converted back.
I'm not like this signal image.
I mean, yes, sir. I mean, after applying CNN, we can extract the informative features, the most relevant, I mean, important features. So those features again can be converted back to signal. Can we?
No, how,
No.
once it is like a signal, no image, then it's difficult. This actually, there is another way. What you can do, you can take signal and obtain the time frequency representation. And time frequency representation represents the energy as a function of time and frequency, where you can get the time frequency image. That will give you the insight, more insight about the data. That may be the right direction instead of taking image of the signal.
Okay, sir. Thank you. Thank you so much.
Go to
Sir,
time
one more
frequency
question.
domain, time frequency domain, and you take image there so that you are indirectly your signal information is actually available in time frequency domain.
Okay, sir. Thank you so much. Sir, one more question from a participant. Have you used real-time data? What is the source of data?
Yeah. Actually, this study, whatever we have compared our method with other existing methods in the literature, which have been studied on the same database. So that is why that, but we in our laboratory actually we are also recording signals. We go to hospitals and we get the data. Uh, this ECG, EEG, all we are studying. Source of the data is patients in the hospitals. From the persons we are getting data. And that is
Any more
actually,
question?
yeah. Can you share with us that actually uh, ethical issues, because this permission has been taken from the institute, and we'll talk to ethical committee, and if it is fine, then we'll happy to share with you.
Question. Please.
Can we balance signal in human? What does it mean?
Can we balance signal in human brain? Very intuitive question, sir.
I think number of signals in normal and abnormal cases. Sometimes patients are actually less, and normal people we get more subjects. So in case of patients, we actually have less number of subjects. So there are some actually methods why synthetically you can also generate such kind of actually numbers signals, so that you can have the same number of signals in both cases, normal and abnormal. So like one of the paper that presented, that was the first part, where actually we have shown that approach. Synthetically, you can generate the signals for abnormal activity like seizures. Then you can make the same numbers.
Yeah, they can now. Any other question? I believe there is no more question from the participant side. So, sir, thank you for an insightful lecture. You started with the introduction, very nice introduction about the EEG signals and the pre-processing part, and then uh, explained about the EMD approach and how what are the limitations of EMD approach to deal with this EEG signals, and then you explained very nicely about empirical wavelet transformation technique, EWT, and then how EWT can be extended to multivariate signals. Also, you explained through an example of epilepsy, and then you applied. I mean, you um,
segmented, you created new channels and then extracted features from the modes. Then you take up another problem, EEG spectrum for schizophrenia, and also explain the whole technique, how it can work, how it can find out the proper features from the signal, and then you applied machine learning technique to classify and compare with already established results, and you have got a very high accuracy, and which will help us to to augment, to add some new kind of technique or tools to the same problem, so that we can extend your problem to a higher level. So thank you, sir. Thank you so much for coming, accepting our request, delivering the lecture so nicely, and also we are expecting one more lecture from you after one day. So thank you, sir. Thank you so much.
Thank you very much for this opportunity. I also would like to convey my thanks to participants for attending this talk. Thank you.
Namaste, sir. And I request all the participants, please submit your feedback using the link which is provided in the chat box as well as in the WhatsApp group. So I hope all of you have enjoyed the session, learned so many things, and definitely will apply in your research. Again, after 1 hour break, we will assemble here for the next lecture. Thank you all.
One question.
One question: can we generate networks for synthetic signals?
We can also separate.
Okay. Yeah. Then offline also help. Okay.
Otherwise, you can keep it on instead of trading again. Just leave it on. Just keep it on, otherwise you'll have to join again and again.
Yeah.
Let it be on.
Let it be on. Okay. So, Sati, go to our group.
Yeah, yeah.
This is so hard.
Yes, yes.
And battery is also exhausting. The phone.
Today being the first day we have arranged nothing. So today is the first day that
So, you can.
a lot of them have their own.
And Anthony, we are putting to our group, but you will clear
Yes,
your thing. Okay, thank you.
But
But you
you
start, you start the next season from 2 o'clock.
But we are notified to 15 now, so they will join.
Start playing the video.
It is on. Whoever will join, they can log in and we'll have you start the one of the video. Okay.
Let's start at 2:15 only, but by 2 o'clock one side video. Yeah.
No, lecture will start at 2:15.
Yeah.
Before that, only one video. You have the video, no? The same video you will play or some other video.
Next session again will come here.
You can remain locked in and
If we,
you can remain locked in.
It's better to see when you go to my MC, they will continue the sound and all
Yes.
disturbing.
Disturbing, right?
Next session, such a move.
ये जो आ रहा है change
The
over.
moderators can come and
Moderator can come here. And center form.
Yeah.
If you find problems for wrapping up, just
That's okay.
okay.
ठीक है. Ma'am, you won't have that there.
Or if you want me to
If you
have
want-
video, then
If you want, you can have.
okay. I'll have with all of you.
Chicken chowder. You eat chicken or not?
Yeah. But session was very nice, no?
Yeah.
So informative.
You understood everything then.
Yeah, because my area.
Oh, yeah. Sir, sir.
Yeah, my one of my student is working in this area,
That's why.
and one more also started working.
That's why it was very for sure.
Yeah, definitely. At least you learn few words. That's it.
Next session is so interesting for them.
Next session is what? Next summarization, yeah. For you, I think you will that one. Okay, you will that one. If he finds any problem, you will that one.
Tomorrow session, the next summarization, there will be
Oh, next session is what?
next session is on
Traffic monitoring system based on deep learning. Ah, nice one. All of you just, I think people love, it's a real life problem. Okay, how the real life problem are being there, you can, at least that much you can understand.
next session is on deep learning. Tomorrow, next
you.
summarization is machine learning.
Already you have started A data, little bit about some computing. So I think you will get to, I mean, understand quick and pieces of the application.
We request your friends to watch the EEG for the experiments.
Here can we put this one?
Yes, yes.